Hi there, get ready for the Maclaurin expansion. So it's named after Scottish mathematician Colin Maclaurin, and it's basically about a polynomial that can be written with positive integer powers of x, and there's no highest power. Okay, so it's an infinite polynomial written as something plus something x plus something x squared plus something x cubed, all the way up to whatever you want, x to the power of 100, 1,000. Basically, it's an infinite expansion, keeps them going. So your generic term here. Because we're going to run out of letters of the alphabet, rather than use A, B, C for the coefficients, use A1, A2, A3 for the x squared, x cubed terms, and then A0 for the constant term. So that is our general polynomial. It could be a quadratic. It could be f of x is 2 plus 3x minus 4x squared. Okay, but this is a general polynomial written this way, and then we're going to do things with it. And I'm going to show you that it can be written essentially as this, and that's what we call the Maclaurin Series Expansion. So to do that, we're going to need to differentiate several times. So this needs to be infinitely differentiable, hence why we'll be using positive integer values for the powers of x. I'm not going to explain to you right now why it wouldn't work if, for example, you had x to the power of 1.5, but you'd figure it out. Okay. So here, starting with f of x equals that, we're going to differentiate, and the first derivative, f dash x, we're just going to get a1, because a0 is going to cancel, plus 2x times a2, written like that, and then we're going to get 3x squared, a3, written like that, and you can predict the next one. It's going to be 4x cubed times a4, but we don't really need the next one. But we'll do the rth term though, as it's called, and so that's going to be rx to the r minus 1 times by ar, which is that. Okay? And then the next derivative, so a1 is going to be 0, and then you're going to end up with 2, a2, and then this will be 2 times 3, that's important, 2 times 3, a3, x, and again you can work out the next one. This could end up being that times 4, because you have the fourth power, the power will be 4, and then multiply it by 4 and 4 it through, you get 24, but we don't need that term. And then the rth term here is just going to be r minus 1 multiplied by that, and then x to the power of r minus 2. And then the third derivative looks like this, so there it is, so that would be 0. And notice how I've just lined it up so that you can see how continuously differentiating this becomes this, becomes this, becomes this, all the way down to this one. This becomes this, becomes this, becomes this, okay? And then that's enough for us to see a pattern, so we don't need to find a fourth derivative, because I've got a pattern there. I'm going to see what's always happening is we're going to end up with, to begin with, like r, and then r minus 1, r minus 2, r minus 3, r minus 4. So the rth derivative, that is when you differentiate r times, is going to be this, r minus 1, r minus 2, r minus 3, all the way down to times by 3, times by 2, times by 1, which is the same as r factorial. So all of that is r factorial. And you can check this, when I said 3 times 2, it's 3 factorial. The next term, I said times by 4, that would be 4 factorial. 24, working backwards, 2 factorial, and 1 factorial. Okay? So you can see the generic derivative there, written like this, incidentally, f and then brackets r. We run out of dashes, or basically we don't want to include a lot of dashes. So the notation is, after you've done 3 dashes, you have f4 in brackets, f5 in brackets for the fourth, fifth derivatives, and then you get this. So that's all very good and well, but what is that actually going to help us with? Well, I'll show you on the next slide. So this is just a reminder of those derivatives we've actually got. And what we're going to do is we're going to substitute x equals 0 into both sides and see what happens. So when I put 0 there, I get f of 0, and then all these terms are going to cancel. Okay? You're just going to end up with a0. So you'll get f of 0 is a0. And then the next one, we get f dash 0 is equal to a1, because all those are going to be 0, because they've all got terms in x. So that's the next one. Something slightly different for the next one, because there's a 2 there. So it would be f double dash 0 is equal to 2a2. All those will be 0. But what I want to do is I want to make a2 the subject. Okay, so I'll just rearrange that, and I'll get f double dash 0 over 2. And bear in mind the factorials that I said, it's better at this stage to write that as 2 factorial. And then the next one, so here I've got 6, which of course is 3 factorial. When I put 0 into that, all these terms afterwards is going to be 0. So I'm going to end up with this result. So f triple dash 0 is equal to 3 factorial, a3. And then if I rearrange that, make a3 the subject, I've got this there. And then for the rth derivative, so I've got that, and I'm just going to end up with the result that f r of 0, the rth derivative, when x equals 0, is just going to be the same. There's no x term there, is that? So r factorial ar. Okay? Rearrange that, ar is going to be this over that. On the next page is just a summary of that, okay, including the original line we had, which is the polynomial expression. Now here's the critical bit. What we can do is replace the a0 there with f0, a1 there with f dash 0, and so on. So in doing so, you're going to get this, and then replace the a2 with that for the x squared term, and then a3 with that for the xq term, and so on. And then for this term, replacing ar with that. And bring it back to how it started. That is our Maclaurin series expansion. Okay. So that's where it comes from. What I'm going to do later on is show you some examples of how that actually works. I'm hoping you got something out of it. Thank you very much for watching, and I'll see you again. Bye-bye.